You're getting a zero. You're getting a zero. All right, so the first question is the heat of combustion for 1 mole of propane. Now, again, the good news is it actually gave you the formula for propane, and most of the organic molecules they do. C3H8 at standard conditions is negative 2,046 kilojoules. Now, something Jacob brought up that I think is a good thing to bring up at this point. I do want you to write this on your partner's paper. Behind the letters KJ, what should there really be? Per mole of reaction. So do write that for them, please. No, remember this is old. This new per mole of reaction is a new thing, and that's why. And again, that's why I put that slide in there. Is you will see some things that don't have it because it's a new thing for AP. And again, this worksheet was not designed for AP, and so some people don't do that. Because that's per mole of carbon dioxide. We're talking about per mole of reaction. I understand that. Okay. All right. So part A, write a balanced chemical equation for the combustion of propane. Now, hopefully, you know that the three major things about combustion reaction is it has to be oxygen, and you have to have the products of a hydrocarbon of carbon dioxide and water. Now, some of you will remember this. I'm going to help teach a faster way to balance combustion reactions. Anybody remember that tip that I taught you last year? Say it again. Very good. Double the coefficient on the hydrocarbon. And again, you don't necessarily have to do it on this, but I'm telling you, most combustion reactions, this will make it go a lot faster. So if you double the first one, so I've got 6 carbons. Just stay with me, okay? I've got 16 hydrogens, so I need 16 hydrogens. I've got 12 plus 8 is what? 12 plus 8 is 20. Well, what's half of 20? 10. Now, again, if there were an odd number, what would you do? Leave it alone. But is there an odd number? No, so what do? Reduce it. Again, I'm going to tell you, a lot of combustion reactions have the double number. And you don't have to reduce, but there are some that you have to go back and reduce. So we've got 1, 5, 3, and 4. Again, you could have just blown through that without doing it, but it makes it a lot faster if you do it, because what would have happened had it not balanced the first time? What would you have gone back to do? Then you would have had to try to do it again. If you go ahead and start with this, it's a lot easier to start with this and reduce than it is to do it, figure out all that math, and then have to redo the entire thing again. Yes, sir? You could have halved it. You could have put the half. Yeah, you could have. I don't like half coefficients. Those all have always bothered me. But again, it is what it is. All right, so so the person doing this, the purple numbers in front, that's worth 2 points. So give them 2 points for that particular answer. Okay, 2 points for balance equation. All right, B, calculate the heat of formation of propane. So what's the specific question they're asking you for? They're asking you for the delta H formation of that thing. Okay, so here's the deal. They told you in the stem, it says the heat of combustion for 1 mole of propane is so the delta H of the reaction is equal to negative 2,046 kilojoules per mole of reaction. Okay, and they're asking you about part of this. Whose law do we need in order to solve this? Hess's law. Very good. So we take Hess's law. So we've got the delta H of the reaction is equal to the sum of the delta H of the products minus the sum of the delta H of the reactants. Okay? 2 very important things about Hess's law. You grammar Nazis, is that the correct? Yay. Okay? All right. So the first thing, in Hess's law, is it possible to have zeros? Yes. Okay. Zeros are for what? Standard states. Okay. That's rule number 1 that applies to Hess's law. Rule number 2 that's also important. Peyton, what's very important about Hess's law? I think you messed up. Logan? Thank you. Okay. The second thing are the coefficients matter. But Peyton, it's Women's Liberty Day. You should be able to freely express your answer. I could always ask the men, but I chose to ask a woman. All right. to move on. Yes, I'm sorry. Shh, stop. Shh, 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 shh. That's right. She did tie. None. All right. Shh, 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 shh. You got it. Thank you. Nick, stop. Now, so we've got the delta H of the reaction is equal to, and again, the products. So, you got to help me out. Oh, wrong button. The coefficient of carbon dioxide is 3. So we've got 3 CO2s. Hey. Okay. So we've got 4 waters. Okay. And that's all going to be minus. Now, when we go back and we look at this, I keep hitting the wrong button. Is there any product or reactant that we can leave out? Oxygen. So we don't need this. Okay. So the only thing we're going to have is 1 C3H8. That bother you? I'm sorry. Hey, Peyton, so what are we going to solve for?
Stop talking to me.
Then stop talking. Stop.
I'm asking about work.
This is not work. Thank you. All right. Now, they tell you that this is negative 2,046. Now, in the problem, they tell you that gaseous water, which I don't need yet, carbon dioxide is negative 300. Excuse me. What did I? All right. So I've got. Dang. Yeah, I don't feel good either. So negative 394. Now I'm going to leave out all the units. It may be a good idea to. No, it's not. You got it backwards. Did you mess that up? Okay. So if you read the problem says calculate the heat of formation propane given that gaseous water is negative 242. So it's not in the same order that you probably wrote it in, and that's the part where students mess this up every year. Okay, they swap these numbers. So if you put the 242 with the 3 and the 394 with a 4, then you've done it wrong. It's not. This isn't tough. It's just making sure you follow the right steps. Now the purple and the blue swap completely fine, but the 3 has to be with the 394 and the 4 has to be with the 242. That does not. That's the important part. The order you put them in does not matter. Yep. Okay. Is that how you did it? Okay, that's perfectly fine. All right. Now, when you solve all of this, okay, the first thing you do is solve what's in brackets, and that came out to be with what? If anybody write that number down? All right, so negative 2150, and then minus x. So what do you do with that negative 2150? Add it to the other side, and then finally, what do you do? All right, so the delta H of formation of C3H8, by the way, I should have put all the not symbols in there, is going to be equal to what? Negative 104 kilojoules per mole. All right, so, yeah, I did add the not. It does either way. If it has not, include the not. So here's the deal. Here's how you're going to score this. You're going to give 1 point for something that shows some sort of number substitution. Okay? Something that shows some sort of substitution, whether they wrote the first line or whether they wrote the second line. Okay? Some sort of substitution. You're going to give 1 point for the correct sign and number, so negative 104, and you're going to give 1 point for the correct unit, and it has to be per mole. Okay. Today and today only, I'm being lenient. From now on, because what was the question? You have to put, hang on 1 second, the delta H, because the question was of propane. Okay? Yes, sir. No. No. Yeah. If the number is wrong, then the unit doesn't count. It has. That's basically, yes, 5 points. Then that's wrong. The sign has to be right. Hang on, Mitchell. Say that again. Okay, bring it to me. Yes, yes, ma'am. Sarah, come to me. No, that's right. Oh, that's right. Yeah, that's all right. 1 point, just for a substitution. The answer to this. Okay, so this is number 20, and again, I want you to write this stuff down. If you don't have enough room, just kind of put it at the bottom or draw an arrow. So the question is, which of the two formation reactions? Now my question is, how do you know that these are formation reactions? It forms a single thing. So this, we don't call this formation reactions. We call them what? Synthesis. So it's a synthesis type of reaction. So which of the two synthesis reactions would you predict to have the largest exothermic heat of formation? Now remember, this is important in terms of energy. The amount of energy that is released is also the amount of energy required to make something, right? Because exothermic means bonds are being broken, so energy is being released. So my question, again, now can be restated as which one of these would release the most amount of energy? So to break this, excuse me, check. Let me restate that. I misstated something. Write that down for me. So remember, when bonds are formed, energy is released, okay? So exothermic means bonds are being formed. Now, based on that statement and that statement alone, which one do you think is the correct answer? The one on the left. Very good. Now, we need to talk about why this is the higher. That's terrible. Let's change this. Okay. So this has, excuse me, that's probably a terrible way to write that, isn't that? Remember, delta H is the enthalpy of the formation. Because higher delta HF is a bad way to look at it. It's more exothermic. Either way, I don't like the word higher because it's technically a more negative number. Does that make sense at all? It's most negative. It's the highest absolute value. Either way, it's just an absolute value. But when you think of higher, you think of not negative numbers. You can put the most negative. You can put the farthest from zero. That reaction is the one that's more exothermic of the two. Okay? And here's why. Totally misspelled that. That's the reason why. That's what I'm fixing to tell you. I promise I'm not going to leave you hanging. That's part of it. Okay, so number one, and I'm going to change pages. So we've got a stronger crystal lattice. All right, reason number one. No. So that's number one. Not most atoms, more atoms. More atoms equals more polarizable. Now, that big fancy word at the very end, what does polarizable mean? The ability to become polar, right? Now, because you have more atoms, you become more polarizable. What specific part of the atom makes it charge differentiated? Very good. So we also then have more electrons. So something can have stronger poles than the other pole. Does that make sense? So let's pretend you've got a molecule with 100 electrons. Well, what is the most polar point that it could become? 99 on one side and 1 on the other, right? What if you've got a molecule with 300 electrons? You can have 299 and 1. Which one would have stronger poles? The one that has 300 electrons. Same concept here. The more atoms, the more electrons, the more polarizable it can become. Does that make any sense at all? Let me draw a picture then. So let's pretend that I've got element X bonded to element Y. And this has a total of 100 electrons. Again, I'm making stuff up. And all of a sudden, you get this occurring, right? This polar thing. At some point, do you agree that the most polar it could be would be 99 electrons versus 1 electron? Okay. Well, what happens when you have a different one? You've got B and C, and it's got 300 electrons going around it. What's the most polar it can become? 299 versus 1. So do you see how this one has a stronger polar end than the other one? Okay. Does that help seeing the picture now? Okay. So this is why it's stronger, because the poles are more different. That's a terrible way to say that. You get it. All right. So the second reason is because Al is 3 plus versus Mg is 2 plus. Now, do you agree that these are both the cations in these two reactions? Right? Because it's Al and Mg. What are the anions in both? Oxygen. So, you have Al 3 plus, and what's the charge of oxygen? 2 negative. And over here, you've got Mg 2 plus and O2 minus. So do you have a differing charge distribution? That aluminum is going to pull those oxygens a little bit closer because of the strength of attraction. Does that make sense? Yes, no, maybe, possibly? Okay. Because there's a difference in charges. It's going to be a little bit stronger because the net charge is going to be different. Yes, no, maybe, good? All right, fantastic. These are the reasons. Yep, these are the two reasons. Because one compound has more atoms, which means it's more polarizable, and because of the aluminum's charge is higher than magnesium, so it makes it stronger. Yeah. Well, the crystal lattice is stronger because of these two reasons. You could say stronger crystal lattice. I would include one of these two reasons of how you know it's a stronger crystal lattice. So the stronger crystal lattice is the reason, but these are the whys. Okay, and they want the whys, not the reasons. Because you can state a fact, but you got to explain your fact. All right, if y'all pass all those this way for me, Jacob, if you'll collect those. All right, so yesterday we left off, we're almost through this, but remember, we talked about these different reactions that have the ability to go through multiple steps. Now, instead of saying the term multiple steps, we have one word. It starts with an M. What is that called? It's a mechanism. Very good. So we have these different reactions that even though the entire reaction can be exothermic, the mechanisms could include an endothermic aspect to it. So, prime example. Let's look right here. Again, this is the exact reaction you guys just did, isn't it? Yep, and this is why I parlayed that question into this. And so if you look from reactants to products, what is the sign of that delta H? So that tells you that this reaction, based on the delta H and the delta H alone, is what? Exo or endo? Exactly. So how do you know that experimentally or thought-provokingly? Because it's combustion, right? Anytime you have a gas grill, it's combusting. That's releasing heat. But notice what happens. Look at the first mechanism step right here in yellow. What's the sign of the delta H? Positive. So even though the entire reaction as a whole has an exothermic value, can it potentially have an endothermic aspect to it? Yes. Okay. And notice what happens. You have decomposition. So the very first word you wrote a minute ago was you said exothermic happens when what happens to bonds? When bonds are formed. Well, what happens when bonds are broken? Think about a karate board. What got into the injury? Energy goes in. Well, this says decomposition. What is decomposition? To break apart. Well, to break something, what do you do with energy? Put it in. So decomposition, does it have an endothermic value? Yes. Well, what are we doing to these two things? We're breaking propane down, correct? Well, then notice what happens in step number 2, which is in the orange circle. What's that first word? Formation. Do you agree that that is making, creating? So that is bonds are being formed. So energy is what? Released. Well, what is the sign of your delta H? Negative. And notice what happens. Even though the first step goes way up, notice what happens in the second step. Where does the blue line come down to? Past where you started. Does that make sense? And so then the final step takes it even farther down, which again, you also have formation again. So even though the entire reaction is exo, it can have an endothermic aspect to it. Same thing is true. What if the entire reaction is endothermic? Can it have an exothermic part within it? Yes. The last little question I want to ask is, where are all of these steps taking place? Why can't we see these steps? Where are they taking place? They're taking place right there. Remember, they're in the arrow, so we don't have to show them. And so I think the sum of these equations, so I don't know what this is called in math, but what happens when you take all three, I guess it's cancellation maybe? When you take all three of these to get a goal or summary equation? Is it summation law? Well, all right. Well, there is a law to it. So here's what I'm talking about. What happens when you have 3 C's on one side and 3 C's on the other? They cancel out. So those will cancel. What happens when you have 4 H2s and 4 H2s? What happens? They cancel out. Okay. Well, can we cancel anything else out? Nope. So I'm left with C3H8. How many oxygens am I left with? 5, which notice there. And how many carbon dioxides? 3. And how many waters? So you can do all these summation laws with these mechanisms. And so we started with the top reaction. We saw the mechanism and still ended with that reaction. Does that make sense? So what we're fixing to get into is calculating the delta H using the mechanism laws. Okay. So here's what we had. This first reaction was for the first mechanism. The second part was, take that back. I'm completely backwards on this. This is the delta H for the entire thing, not the steps. So I have 2 questions. Number 1, why is the H for water 0? Standard state. Notice what state of matter that it's in. Liquid. And when water is at its regular room temperature, what state of matter is it in? Liquid. That's why water is 0. Okay. Number 2, why wasn't the final answer divided by anything? So why was this 2219 not divided by anything? Very good. Because what did you start with right here? You started with a 1. Hypothetically, what if it had been 2, 3, 4, or 5? You would have divided by that number to get. But why is that important? What would the final answer have been? In per mole of reaction. And so that's why you would divide it if there is a coefficient there. Okay? Jacob, does that make sense? Okay. All right. So this is Hess's summation law. So enthalpy is not dependent on the reaction pathway. So the reason that this is true is because this is, wow, that's really bad. I want this, and I want this. Hopefully this isn't already written on there because I'm wasting my time. So when it tells you something is not dependent on the pathway, that tells you that means it is a state function. So again, No matter what happens in the arrow, is it going to get to the products eventually? Yep, doesn't matter how it's happened. If you can combine several chemical equations that will add up to give you the desired overall equations, you can, what does sum up mean? Add all of the delta H's for the overall for the individual reactions to get the overall reactions. When we get to kinetics, we're going to do this exact same thing. We did this in equilibrium as well. So you've seen this before, but it's looking at it from a different perspective. Okay? But here's the pain in the butt part about this one, is that sometimes these reactions have to be rearranged, changed, added, multiplied. So you remember those times when we flipped the equation, what did we do to K? We inverted K, right? When you flip the equation, you flip K. What happens when you half the coefficients? Took the square root of K. Very good. What happens when you double the coefficients? You squared, not doubled. Okay? So it's kind of the same concept, but it's a little bit different. So we can rearrange the equation so that reactants are products on the appropriate sides. If an equation had to be reversed, what do we do to the sign of delta H? We flip the sign. But how is this different from equilibrium? When you flip the reaction in equilibrium, what did you do to K? There wasn't a sign, right? What did you do to it? You took the reciprocal of it. Okay? I think this may help. So let's actually do this because I don't actually have this slide. How do you spell reciprocal? Okay, so that's the first one. If I were you, I would either take a picture of this at the very end, or I would write all this down. Hang on one second. I need to look at something real fast. We'll come right back to this. Tomorrow you have to sit over there. I've been begging y'all for 3 days to stop, and y'all won't do it. What do you mean, which one's which? Does that help? No, so you can do this to both of them. But the blue goes with the thermo, the orange goes with the equilibrium. So if we're doing thermo reactions and you flip the reaction, what do you do to delta H? You flip the sign of delta H. But if you're doing equilibrium, you take the reciprocal of K. If you change the coefficients in thermo, you multiply or divide delta H by the change. But if you're in equilibrium, you raise K to the power of the change. I probably need to write that. And I've got one more I need to add. I probably need to make this a slide, don't I? I will. I'll go back in and add that. Honestly, to be genuine, this is the first year I've ever thought about comparing the two, because this is the first year I've ever taught equilibrium before thermo. I think that was a good call. had one class that did awesome. I had one class that did terrible. 7th. Because they don't listen. It is a bad time of the day. But all right, the last thing. I'll come back to this if you don't get it. To the change. Raise K to the power of the change. Now, this is the very last thing that you could do. And again, I'm comparing the two because there are some differences. What if you need the total value of the reaction? And I mean delta H of the reaction, and I know you've never saw this before, but I'm just using it as an example. What if you need the K of the reaction? And again, this is only when we're talking about multiple steps. If you need the total delta H of the reaction, what do? You add the H's. What if you need the total K of the reaction? You multiply the K's. Now, why are there differences? Why is it? I don't know. I just know these are the rules. And I can see why it's confusing and how it's confusing. And why aren't the rules all the same? I'm going to kick those people in the shin. No. Because remember, this is the part of the reaction. This is totally different from Hess's law. So remember, the mechanism we saw had 3 specific parts to it. You take those specific mechanism parts and add them all together to get the total value. And I'll go back and show you. Do I need to go back to the previous slide? Parts of it. All right. So here's the deal. The last thing that I want to sum this whole thing up is what's the last thing that you wrote down is if you need the total delta H of the reaction, what did you do with all the H's? You added them all up. So here's the deal. If you took that number, and that number, and added all of them up, what do you think you would get? This number right here. So that's how you can calculate all of these delta H's when you have them in steps, in mechanisms. Okay, so that's kind of what I wanted you to see out of this. So let's look at a particular problem. So here's again, this is the part that makes it challenging. Is that are the reactions always going to be perfect like you need them to be? No, you may have to flip some things around, and that may be a challenge. So here's the deal. So these 2 steps, do you agree that this is going to be, let's make this step 1, and this is step 2. So this is occurring in a mechanism. And this right here is what we're trying to get to, this down here at the bottom. So this is our goal equation. So my first thing is, does step 1 match the goal? Does step 1 match the goal? It's close, but what's wrong? The last, right here. This is a 2 and that is a 4, so it doesn't match. Does the second step match the goal? No, but can we do something to both of them to make them match the goal? Yes. What can we do? Put them together. So if we add these 2 together, first of all, will anything cancel? Remember, use the arrow as an equal sign. I'm trying to find commonalities on both sides. Do you agree that that's common to that? Yes. So if they're common on both sides, what can you do? Get rid of them. Why did that not keep finishing? So I'm going to cancel this and cancel this. Is there anything else that's on the opposite sides that I can get rid of? No. All right, so I'm going to bring this down. So I've got Sn plus. Well, here's the problem. I've got 2 of these on the same side. So what do you do with them? Coefficient. So I've got 2 Cl2s, and that's going to give me SnCl4. Now, does this match our goal equation? Yes. Did we flip any of the reactions? Did we change any of the coefficients in the mechanism? No. So how do we find our total delta H? Add these two numbers together. So when you add these two numbers together, what do you get? So this is delta H of the reaction, negative 511 what? Very good. Kilojoules per mole of reaction. Yes, ma'am. Yes. Yes. So let's hypothetically, what if we flipped mechanism 1? What would you do to delta H1? You would flip it to positive 325. Okay. Same kind. What if we had double the coefficients of mechanism 2? You would double that. Okay. So does this make sense? Now this is easy, straightforward, pretty simple. Let's look at one that's a little bit more challenging. All right. So we've got how many steps to our mechanism? 2. And we need to make it match our goal equation. All right. So here's the deal. We've got solid water as a reactant. We've got H2 as a product. We've got half oxygen as a product as well. Now, is there anything in our 2 steps that can be canceled? Very good. All right, 2 H2Os. They're not. Liquid and liquid. It is. All right, now, so these 2 can be canceled, right? Now, so when I bring what I've got left is 2 waters, 2 hydrogens, and an oxygen. Does that perfectly match our bottom number? No. What do? I've got a half both of them. So this is going to go away. This is going to go away. And what's going to happen here? That's going to flip to a half. Well, then what do I do to my delta H's? Well, you got to half them first. Okay. So this is going to be 6. Well, I would half them then, Adam, just in case. I don't trust it. Because that may not be all you have to do. Okay. And what's half of 572? Somebody have that real quick? Jacob. 572 divided by 2. 2. 572 divided by 2. I just want to make sure. I don't believe y'all sometimes. All right. So when I do that, I will have my goal equation of H2O going to H2 plus 1/2 O2. Okay. And now I'll add these up, and that's 292. Does that make sense? Now, it's 292 what? Kilojoules per mole. All right, so tomorrow we will look at one more. This was going to be a little bit more difficult. This is your warm-up tomorrow. Be ready to go.